the final type of process we're going to look at is an adiabatic process. As a reminder, that one is where Q is equal to 0 for the process. So in this case, delta U is equal to W. The only change in internal energy can come from work that's done on or by the system. Now we know that W is equal to minus P dV. We know that delta U is equal to CV dt, right? These sort of are our two different parts. So we can say that we can sort of look at those separately, but we can also combine those for an adiabatic process to tell us a little bit more about that relationship between temperature and volume. So we know that CV dt is equal to minus P dV, if we keep this in differential form. We can make some substitutions. So on the left-hand side, we can write this in terms of a molar quantity. So like I mentioned in the previously about heat capacity, this version here is just the heat capacity of the entire system. What we usually look at is our molar heat capacities, which we'll write the same way we did a molar volume. We'll put a bar over the top of it. So this is what's the heat capacity for a mole of our gas. So then the total heat capacity would just be how many moles of gas do you have, N, times the molar heat capacity, times dt. So we can substitute that. We can also substitute the ideal gas law. We assume this is a reversible process. We can use the ideal gas law to write out P. So we can say minus nRT over V dV. Now we have n's on both sides here. Those will cancel out. And we can go ahead and integrate each side. So we can integrate from T1 to T2 on the left-hand side of CV bar dt. And we can integrate from V1 to V2 RT over V dV on the right-hand side. One thing we'll do actually, we want to collect all the same, right? So this T is sort of out of place here. All the other T's are on this side, so we'll collect all the T's together. So we'll write this instead as, before we integrate, put the T over here. Okay, and then each of these are pretty straightforward to integrate. So this is just basically 1 over x like we've seen before. Okay, so we'll get CV bar, that's just a constant, log T2 over T1 is equal to minus R log V2 over V1. So if we integrate both sides. Now we can go ahead and rearrange this a little bit. So we'll put all the constants on one side. So CV bar over R times log T2 over T1. And then we can use properties of logarithms. We'll go ahead and do this now. The negative of a log is the same thing as switching the fraction inside of the log. So we can write this as log V1 over V2. And now we can reorganize this a little bit more. Use another property of logarithms. We can say that if you multiply a logarithm, that's the same as the log of the thing inside of your logarithm raised to the power of what's multiplying it. We're preparing to get rid of these natural logs. And if we take the anti-logarithm by taking the exponential of both sides, we'll get T2 over T1 CV bar over R raised to the CV bar over R is equal to V1 over V2. And this is a relationship between volume and temperature that applies for an adiabatic process with an ideal gas. So if you know something about, if you know 3 of these things, right? If you know the initial temperature and the initial and final volumes, you can find the final temperature, or vice versa. If you know the initial and final temperature and one of the volumes, you can find what the other volume is. So this gives us a way to find things out about volumes and temperatures for an adiabatic process with an ideal gas. All right, and so this is the last of our sort of specific types of processes we're going to consider. And you may notice that in these lectures we haven't put in specific values. We haven't looked at 5 liters of gas and temperature of a specific number. That'll be for you to do in your homework assignments, so you'll get the chance to practice with this and find actual values. And we'll do some practice with that in class as well. One important thing always with these, keep track of your units. Make sure you're using the correct units for everything, and everything cancels out as you're working through this.